So if you can see the screen, say yes in the chat. If you cannot see the screen, say no. So can you see the screen right now? Okay, yes, very good. So let's start with the homework first. So today will be lesson 2 of exponential and log functions. And today we're going to be introducing to logarithmic functions. So we're going to go over homework, review, go over the introduction to logarithms, and go over some practice problems. So let's just start with the first homework problem. So I'll give you a few minutes to do this, then I'll walk you through it. Okay, so let's go over this one. So who has the answer to this one? This one is not too hard. Okay, so this one is 0. All right, let's see if it really is 0. So who can volunteer to help me solve this? Do I have any volunteers? Okay, Dan Lu, can you solve this?
So I made it 2 to the power of 2 times 2 times x minus 3, which is 4x minus 12.
Okay, yeah.
And then for 8, I made it 12 times 3x minus 1.
What? Oh, yeah, bro. 12. Like this, right?
Yeah. So 36x minus 12.
Okay.
And so I think the only answer is 0.
Right. Because once you move 12 to this side, it's going to be 4x is equal to 36x, and that's just 0. Very good. So this answer is 0. So the main point is make sure you have to get the same base on the bottom, so then you can compare these. And once you get the same base, you can then set the exponents equal. That's one of the properties that we learned last class. So let's do the next one, and this is about compounding rates, I think, right? Right. Okay, so just do this. And then I'll go over it in like 4 minutes, or yeah. So this one shouldn't be continuous compounding. This one is just compound interest. Okay, so let's go over this one. Do I have any answers for this one? 92,709,068. That's very precise. Okay. So let's do this one. Do I have any like a different volunteer this time? Who wants to volunteer this time? Do I have any volunteers? How about Kaylee? Kaylee, can you do this problem? Shouldn't be too hard.
Um, so the formula is A equals P times 1 plus R over N, and then to the power of NT.
A is equal to what?
P times 1 plus R over N
Okay, yeah.
power of NT.
Yes. Very good. So you just put it into this formula, right? It's compound interest, right?
Okay. Then we get A equals 100 times 1 plus.
You mean 1,000?
Oh yeah, 1,000 times 1 plus 0.1 over 12 to the power of 12 to the 10. 12 times 10.
Okay, so if you calculate that, let me see here. 1 plus 0.1 over 12, and then you take that to the 120th power multiplied by 1,000 is not going to be 9 million. Whoever said that? Making money out of thin air. Anyways, it's gonna be $2,700 approximately. If you compound 10% every month for 10 years, I mean it's pretty good if you more than double your money, right? So I don't think you're gonna get $9 million anytime soon. So make sure your answers are also reasonable, right? So yeah. Number 3, a family wants to invest a sum of money in an account that compounds continuously, such that in 10 years the sum of money will double. What does the rate of compounding have to be? So this one, you have to use the continuous compounding equation. So make sure you do that. Remember what E is, it's natural base. So make sure you use that. Okay, so I'll come back in like 5 minutes and walk you through this one. And then we'll start a review and also learn what logarithms are. Okay, so let's go over this one. So let's see, who can solve this one? Do I have any volunteers? How about Andy? Andy, can you
Okay.
solve this one?
So first, like the formula, right? So then you can do like A, well, so yeah, the formula, and then except you have to make the formula afterwards equal to. So yeah, A equals to P, yeah, times 1 plus,
Are you sure about that?
oh, P, oh, E, yeah, I don't,
It's the continuous formula this time because you compound
oh yeah,
right? So then how do you do it?
I don't know.
Well, the sum of money has to double, right? So that means that if P is 1, which is the principal amount, then A has to be double that amount, which is 2,
2P,
right?
yeah, 2,
So let's just say 2 is equal to 1 times e to the RT. Well, what is T? Time, right? And how many years are we waiting? It's
10,
10 years, right? So what we need to find is R. So we find R, right?
mm-hmm.
Okay. So then we have 2 is equal to e to the 10R. Okay, I kind of messed up here. Huh. You actually can't do this problem yet. Yeah, this problem is a bit too hard actually. Because
I got a little confused.
then you have to take the natural log of 2 is equal to 10R as R is equal to natural log of 2 over 10. And we haven't learned that yet. We will next class though, I think. Yeah, I forgot about that. Huh. Oh, well, I guess you can't just you just can't do this problem yet. But that's usually how you do it. R is equal to natural log of 2 over 10. But you don't know how to do it. So, yeah, I should have just stuck with the original simpler question, but I decided to make my own. And now, yeah, this happened. So, don't worry about that. You'll know how to do it in like 2 classes or 1 class. So now let's review compounding formulas. So everybody should have taken notes on these compounding formulas. So let's everybody just put in the chat the 3 compounding formulas that don't involve E, right? That we learned. Compound interest, doubling time, and half-life. So everybody puts one of those formulas in. Okay, so let's see what you put in the chat. So A is equal to A0 times 2 to the T over D. So that is the doubling time formula. And Andy says P times 1 plus R over N to the N times T, right? So we got 2 formulas, right? So we need one more, and that is half-life. So does anybody know the half-life formula? So this is A is equal to P times 1 plus R over N to the NT. This is compound interest. Right? And then you have the doubling time. So that's A is equal to A0 times 2 to the T over D. And that makes sense because we're basically just multiplying by 2 how many times. So it's just T over D, right? And that's doubling time.
I put the half-life formula into the chat.
Okay, very good. And that should be A is equal to what? A0 times 1/2 to the T over D. So that's very intuitive, right? It should make a lot of sense because we're basically just halving it how many times, right? That's T over D, right? You take the time, the overall time that you're looking at, and then what is the time that actually not T over D. I think the variable I used last time was H, and that makes a bit more sense. It's half-life time, right? You take the overall the overall time and you divide it by the half-life time. So that's how many half-lives you're going to experience over this time of this period of time. Then you that's the exponent of 1/2. So it makes a lot of sense. Also for doubling time, it also makes a lot of sense. It's the same thing essentially. You just change half and 1/2, right? Yeah, well, double and 1/2, right? So we have another formula, and that is continuous compounding. So that's basically when you take the compound interest and n becomes infinity, right? So you compound infinite times in this time period, right? And we like continuous compounding because it makes you the most money, and everybody likes money because with money you can get a lot of things like ice cream. Anyways, so continuous compounding formula is going to be P is equal to, well, not P, it's going to be A is equal to P times E to the RT, where A is the final amount, P is the principal, E is the natural base, R is the rate, T is time. So does anybody remember what the natural base is? Like E is going to be about 2.718281, and basically it's the limit of x goes to plus or minus infinity. Actually, no, you can't really do that. To positive infinity, x goes to a positive infinity of 1 plus 1 over x to the x, right? Okay. So basically, if you take a strong computer and you compute all this, right? And you compute it to like let's say you sub in 1 trillion or a very big number, right? A very big number for x, then you keep putting it in a bigger x, and it gets closer and closer to 2.7182. So for example, at let me see, this is at 100 million, it's 2.7182817886. At 10 million, it's 2.71828164. At 1 million, it's 2.718280.469. So as you see, as it gets closer, right, it gets, well, as it gets bigger, it gets closer to 2.718281. And basically that's what a limit is, as you're just taking x as a greater and greater number that approaches the limit. So you don't really need to know how limits work yet because that's part of calculus, but that's how you find E, right? So the E that we're using here is going to be also an integral part of logarithms. So make sure you know what E is. Right. So I guess we can now start to learn about what logarithms are. So the introduction to logarithms. The logarithmic function is basically the inverse of the exponential function. Right, so the inverse of the exponential function, and we've learned about inverse functions before. You basically, right, replace the x with the y because you change the domain in the range, right? That's what an inverse function is. For example, let's say you have this function right here. The inverse of this would be this. Basically, what you do is you replace the x values with the y values and the y values with the x value. Basically, you swap the x and y values. That means, it also means that you reflect the graph over the line y is equal to x here. So remember that you reflect the graph over y is equal to x. So you can visualize that later. So instead of y is equal to b over b to the x, it's going to be equal to x is equal to b to the y, right? Where b is greater than 0 and b does not equal to 1. And so basically f of -1, well, f inverse of x is equal to the log base b of x, right? So how we look at this is x is equal to b to the y. So we need to find what y is, because y is equal to f of x, or y is equal to f inverse of x, however you want to look at it. So you need to find y, and the notation we do, we look at this, right? So the notation here is y is equal to log base b of x. What we do is we move the b, and that becomes the base of the log, right? Because we call that the base because b is also the base of the exponent, right? So then you move that over and you can see it's the base of the log, right? So one more thing about log. Actually, I think we'll talk about, let me see if we ever talk about it. So yeah, we'll talk about how to solve logs later on when we talk about properties. So just know how to rearrange a log for now. And let's go back to the homework problem. This is how you find r, right? So since you have an exponent here, 2 is equal to e to the 10 times r. Let's see how you would rearrange this. How would you rearrange this? So Kaylee, can you help me on this?
Okay.
So how would you rearrange this? Just like the log that I just did. E is
I
the base, right? So you move it.
It's 10r is equal to e. Wait, no. 10r is equal to log e to the second, I think.
Yeah, so you say this log base e of 2, right? So 10r is equal to log base e of 2. So make sure you say it like that. That's how it reads as. So basically, you take the log with base e. And so everybody get out your calculator. If you get out your calculator, if you have a scientific calculator or anything above that, like a graphing calculator or any fancy calculator, you'll have a log button. So search for that log button, right? And it's gonna be somewhere, I think. You're either gonna have ln or log, so log or ln. They both work. So, and then find the log button, and you can find the log base e of 2. By the way, log base e of x is going to be equal to ln of x, because log base e is just called the natural log. So these are the same. So the ln button will do the job. So this is ln of 2. So basically now you just divide by 10. So that's how you arrange it. Log, right? You move it to the base of the log. So that should be pretty easy to do. So now let's look at one of the graphs of a log function. So let's say that you have an exponential graph right here. So y is equal to 2 to the x power, and y is equal to log base 2 of x. So these are inverses, right? These are inverses. So now if you look at this, we know that an exponential graph always has to pass the point 0, 1, right? Well, a simple graph has to, because when x is equal to 0, then y is equal to 1, right? So that's what an exponential graph will look like. And now let's draw the line y is equal to x. What you need to do is you need to basically reflect this over this line. So this time the reference point will be 1, 0, and the graph will look like this. See how you have a horizontal asymptote here, and you have a vertical asymptote here, right? So don't stress too much about the graph of the logarithm. We'll go over graphs of logarithms in like a couple of lessons. So that's basically what the logarithm looks like. And basically, exponential growth is probably how population grows, right? This is the human population. It just grows exponentially. Sometimes, though, growth happens logarithmically. It grows, and then it slows down. The growth slows down. Exponential growth, it keeps getting faster. You grow more and more, right? Like the human population. And logarithms, they grow slower and slower, right? See how the growth, it's barely growing at once x as x approaches infinity, it's going to be very, very small growth. Don't forget that there's also a vertical asymptote here at x equal to 0. For the exponential graph, y is equal to 0 is the horizontal asymptote. So make sure you know where the asymptotes are. So now let's go on to properties of logarithms. So properties of logarithms, there's going to be 10 of them, I think, or 8 of them actually, that I have right here. So let's just look over each of these. Properties of logarithms. Let's just say b, m, and n are positive, and b does not equal to 1. So our first property here is log base b of 1 is equal to 0. So if you ever find log base b of 1, it's always going to be equal to 0. Number 2, log base b of b is equal to 1. And you'll get why this happens in this next property. Log base b of b to the x is equal to x. So why is this? Let's see here. So that's basically how you solve a log. So if you take a log base 5 of 25, it's going to be equal to 2, because log of 5 to the 25 is going to be equal to log base 5 of 5 squared, and that's 2, right? Very good. So that's how you solve a log. Another one, log base 4 of 64 is equal to 3, because log base 4 of 4 to the third is equal to 3, right? So I think we can actually see this. A to the b is equal to c. and a is equal to log base b of c. So if you substitute this a in for this a, log base b of c to the b, right, is gonna, hold on. No. B is equal to a here. Okay, so yeah, b is equal to log base a of c. So we can substitute a couple things in here. So we can substitute a to the b is equal to c for this c. B is equal to log of a to the b. So that's where we get this property here. We also can get another property, which is, I think, the fourth property. And what you got to do is b is equal to log base a of c. What you have to do is you have to sub this in for b in this one. So a is equal to log, no, a to the exponent of log base a of c is going to be equal to c. So that's our fourth property, which is b to the log b of x is equal to x. See, these b's cancel out. That's very nice. If you ever get this form, so these cancel out, right? Because through simple substitution in the definition of logarithm, we can get these properties. Now, we have a couple of other properties here. So number 5 is log base b of m is equal to log base b of n only if and only if m is equal to n. So if you ever get log of 2 is equal to, for example, log of x, then 2 is equal to x, right? So you can set them equal like that. And similarly, log base b, actually, no, not similarly. We're going to start another whole different thing here. So log base b of m times n is equal to log base b of m plus log base b of n. So this is good for simplifying, right? If you ever see two logs with the same base that are adding up, you can actually multiply them and combine them. 7 log base b of m over n is equal to log base b of m minus log base b of n. So if you ever see two logs with the same base subtracting, then you can actually divide them. So very good for combining and simplifying. And lastly, this is also good for simplifying. Log base b of m to the p power is equal to p log base b of m. So what you can do is you can take this exponent and you can move it outside of the log. So these are all the properties. So I'm going to give you like 1 minute to write these down because these are very important. So make sure you know how to do these. Right? So 1 minute to write these down. Are there any questions so far about these properties? Any questions? If there are no questions, then we can always go to our example problems. Okay, so our example problems, I don't have any specifically written down, but that's okay because I have a bunch of example I can pull from. So let's just do the first 4 here, right? So let me see what I have. Let's see. So log base 10 of 10 to the negative 5th. Number 1. Number 2, let's say log base 4 to the 16th. Number 3, log base 10 to the 1. Number 4, log base e to the log base e of e to the m plus n. Number 5, 10 to the log base 10 of 4. Number 6, log of base 2 x minus 7 is equal to log base 2 of 8. 7 log base b of u to the 1 over 3 over v to the 5th. Number 8, log base b of m over n to the 3/5. So just do these 8 problems very quickly. It shouldn't be that hard, or yeah, you should be able to do them pretty fast. So once you get very familiar with logarithms and the properties, you'll be able to do these without thinking, right? All right, so let's go over this one. So who can solve these problems? How about William? William, can you help me with this?
Okay.
So what's the first one?
Number 1 is -5.
Okay.
Number 2 is 2. Number 3 is 0. Number 4 is m plus n.
Okay.
Number 5 is 4.
Okay.
Number 6 is x equals 15.
So yeah.
Number 7 log b log base b of u to the power 1/3 minus 5 log base b u, yeah. And number 8 is 3/5 log base b of m over n.
Well, you could actually
Oh wait, it's
subtract these.
yeah.
Right. Okay, so let's go on to our next one. See, that wasn't too hard. So let's just do this now. So let's see. Let's get some more examples. So how about let's solve these two, okay? So log 10 of x plus log 10 of 9 is equal to 1. Or log 10 of 3x squared minus log 10 of 9x is equal to 2. Okay. So I'm going to give you like 5 more minutes to do these, and then we'll go over these. Okay, so let's go over these. So the first one, what you can do is you can combine them, right? By multiplying them. So you're gonna have 9x, well, no, the log base 10 of 9x is equal to 1. Right? And we know that we can actually move the 10 to this other side, right? 9x is going to be equal to 10 to the first power, right? So then x is equal to 10 over 9. The second one, we know we can divide these, right? So what do we get? That's equal to 2. And we have 3x squared over 9x is equal to 10 to the second power, right? That's 1/2, right, times x. 1/2 times x is equal to 100, so x is equal to 300. Right. So, are there any questions on this? If there are no questions, then that's the end of our class, and I'll see you next week. Thanks, everyone.
Hi, thank you.
Bye. Thank you.
Bye.